I'm Gordon Freeman. You've seen me in such fine quality chemistry educational films as Half-Life and Potential. Is it possible? And is there a standard for standard potential? Today we're going to be looking at one part of electrochemistry, and that's being able to calculate the standard potential when we are looking at two solutions and we're looking at the electrodes that have been placed into those solutions. Okay, so we're going to do three examples for this, and the basic idea is that we would be calculating the voltage, or the standard potential, if you will. Now remember, the idea behind all this is that you have oxidation and reduction chemical reactions that are happening, whereas oxidation, you have a loss of electrons. Reduction is when you gain electrons. Leo the line goes GER or oil rig. Okay, so let's take a look at one of these. So we can look at something like, here's zinc. It's a solid chunk of zinc plus copper with a +2 charge, and it happens to be in an aqueous solution. Whoops, aqueous solution. All right, and we end up getting zinc with a 2+ charge plus Cu as a solid. Well, wait a minute, what in the world is going on here? Well, keep in mind that this would be an example, a basic example of oxidation reduction. If you have copper sulfate in a beaker and you put a bar of zinc in it, you're going to see that the zinc and the copper essentially are going to be switching places, because that zinc bar is going to slowly lose the zinc atoms. Well, what's happening? The zinc is losing the electrons, the copper is picking it up. Now the question is, well, why is that happening? Well, because copper likes the electrons more than the zinc. Okay, that would be an electronegativity issue. Now, but for us here, we're looking at this, so we look at what's being oxidized and what's being reduced. Well, oxidation is loss of electrons. Okay, so let's look at this here for a moment, and you kind of notice, I'm going to break this into two half reactions, because one of the reactions is occurring at the cathode, okay, the positive part of the cell, and then the other is occurring at the anode. Now, in another film, we talked about the idea of red cat, reduction happening at the cathode, and then, of course, anox, which means you have oxidation at the anode. But let's go ahead and let's look at this here for a moment. So ZnS, and we end up getting Zn 2+ plus 2 electrons. Okay, so that's a half reaction. We're only concerned about what's going on with the zinc. Let's go ahead and we're going to use the blue and simulate our copper. So we're going to have our Cu 2+ plus 2 electrons gets us Cu as a solid. So that's our other half reaction. So what's happening? Well, the zinc is being oxidized because it's losing the electrons. The copper is being reduced because it's picking up electrons. So that's what's going on here, okay? Now, in this case, the number of electrons are equal. We don't have to balance anything out for this, okay? But like I said, this is a classical thing. Now, the next thing that we're going to need to do, we need to understand, how do we calculate the potential for a cell? Okay, well, here, if we look at it, the potential for the cell, and they represent that E with a little funny zero looking at the top, is equal to the potential energy of our copper and our potential energy of our zinc. Okay, that's basically it as far as what's going on. Okay? All right, so what do we do? How do we find these potential, standard potentials? These are known as standard reduction potentials. Now, they do have tables. We don't have enough chemists out there that they did all the grunt work on this, so yay for them. We can just simply go ahead and look on the table here, and you kind of notice, if I bring this up, you kind of notice, hey, there's a whole bunch of these here. Yeah, and you can sit there and start looking at the values. Okay, so in this case here, we're going to look at, here is the energy, our electrical reduction, our electrical potential for zinc. And I'm going to look it up on the table here. I got Zn 2+ going to Zn as a solid, okay, and that gives me a value of negative 0.76, and that's volts, okay? That's negative 0.76 volts. On the other hand, on the other side of the coin, we have our same thing, our standard reduction potential, but this time we're looking at copper with a +2 charge, and in this case it's got 2, so we're looking at copper here, okay, with a 2 plus 2 electrons, and that's going to get us a copper that's solid, and that is going to have a value of, I gotta make sure I've got this right, 0.34 volts. Now, so now we have our two potential values here, but one of the things you may notice how I wrote out the reactions in the direction that it's going. In other words, this is the reduction. Well, remember, the idea behind reduction, you're picking up electrons, you're gaining it. Okay, so this is why, this is kind of the values that you have. Now, of course, the problem that you run into is, but wait a minute, this is correct about the copper, because the copper started out as ions in the solution. It ends up picking up these electrons, which it picked it up from zinc, and it became a solid copper. Okay, but then we have zinc. Well, zinc is kind of falling apart here. Okay, and in this case, I want to point out that you have, oops, sorry, that's the wrong side. The truth of the matter is, there we go. Okay. There. Now we got it fixed, right? I wasn't quite sure. All right, now in this case here, we have 2 electrons plus the zinc 2 plus gets us a solid zinc. But look at the direction that it's in. It's not in the direction that it should be if we compare it to our original reaction, which is right here. It started out as a solid and it ends up being oxidized because it lost the electrons in the process. Whereas copper started out being an ion in solution, and then it became a solid, and then of course it deposited, and then you go on from there. And you'd say, but wait a minute, what happened to the electrons? Well, keep in mind they kind of canceled each other out, because what the electrons that left the zinc joined up with the copper and made the copper nice and solid. So the electrons are not really moving around out there. Now, how does that address what we have here? Well, in this case here, because of the zinc, this is going the opposite. We looked at our reaction. The zinc was starting out as a solid, and then it's going backwards according to this standard reduction potential. So that means we got to make this, we have to flip the sign here. We're going to flip the sign, and we are going to make it a positive 0.76 volts. Remember that they're going to go opposite of each other. That would make sense, because you can't have both of them going in the same direction where they both become a solid. That doesn't work. You're not going to have that galvanic cell that's happening. You're not going to have that action. So if we go ahead and we add, remember the E cell is equal to the E dealing with our copper plus the E, our standard reduction potential of our zinc. Okay, in this case here, we're going to go 0.76 plus 0.34. And it's that simple. We just add it up. That's all we do. Okay, and ladies and gentlemen, it's going to be 1.10 volts. So that's it. That is our answer for the copper and the zinc, ladies and gentlemen. Okay, let's see if we can go ahead and let's do another one. Why don't we go ahead and let's do a potential here. I'm going to go for this, so I'm going to go for this next one here. I'm going to shift. I'm going to go a little bit faster because I gave you the underlying idea. Okay, so let's go ahead with it. We're going to go and say copper 2 plus, that's going to be an aqueous solution, plus tin, which is a solid, and that's going to get us copper as a solid plus tin in the form of an aqueous solution. So it's a very similar situation that you had with the zinc, except this time instead of using zinc, we're using tin. That's what SN stands for. It's tin. Okay, so let's break it down into our 2-half reactions. So I don't have to already bore you with the details. You're going to have copper with a 2 plus plus 2 electrons. And where are those electrons coming from? The tin. And then we're going to get copper as a solid. So that's going to precipitate. Okay? You say, wait, how do you know it's going to precipitate? Well, because it becomes a solid at that point. Then, if we look at our half reaction of our tin, which is a solid, ladies and gentlemen, okay, it is going to break down into Sn with a plus 2 charge plus 2 electrons. So this is what we have, ladies and gentlemen, here. Those are our two half reactions. We broke them up again. Which one is oxidized? Okay. The one who loses the electrons is the one that's oxidized. Well, in this case, it's the tin that loses it. It's oxidized. And then here at the copper, it's going to be reduced because it picks up the electrons. Now, let's go ahead and let's see what we have for our values. We're going to go back and look up our standard potential. Now, when you look at the standard reduction potential, keep in mind it's going in the direction of you start out with the ion, you pick up electrons, and you become solid. Right. So, let's look at it. So I'm going to go ahead and I'm going to look at the copper. The copper one here, we start out with our ion plus the electron, we become solid. So our E cell is going to equal, okay, the E of the copper plus the E of our tin. Okay, now since the copper is already going in the direction we want, the value of the copper is going to be 0.34. Okay, it's positive. That tells us that we're going to get some electricity out of this. We're going to get some electrical energy out of this as a result of this. But when we look at the Sn, that's a little bit different because the solid is now changing. Okay, let me go back and find it. Ah, here we are. Okay, when it goes in this direction, okay, when it goes in this direction, it's going to be the opposite. Okay, if it was solid tin forming, if we had this reversed, it would be negative 0.14. But that's not the case here because our solid is breaking up. Okay, it's breaking up into an ion. So guess what? That's going to make it a positive 0.14 as a result. So we add them together, we're going to have 0.48 volts. And that's what's going to happen. Okay, so we looked at our copper zinc battery and we found, hey, we got 1.1 volts out of it. We looked at our tin and copper and we got 0.48 volts out of it. Now, the fact that this is going to be important that the potential is positive, because if it is positive, that tells us a couple of things. One, we can get electricity out of it. Okay, that would be kind of an important thing for us, because if it's negative, then that means we're not getting any electricity out of this. So that's it. That's it with this one. Okay, and okay, let's have a little bit of fun with this. Let's try another one. Okay, I'm going to go ahead. I'm going to do one more with you guys, and this one I'm going to take something completely random, like calcium plus lithium. So we're going to put a lithium bar into a solution that contains calcium ions. It could be calcium sulfate, whatever it's going to be. Okay, and we end up getting calcium that is solid plus lithium with a positive charge to it. Now, in this case here, when we look at our half reactions, what you're going to find, ladies and gentlemen, is that, okay, we're going to have calcium 2 plus 2 electrons is going to get us our calcium that's solid. Okay, and we can look at our standard reduction potential. I'm going to speed up a little bit because you guys should be comfortable with this right now. And that's going to be a negative 2.87 volts. That's what we've got going for us. Okay, but now let's take a look at the lithium. Now, the lithium, on the other hand, notice that it's going from Li, that's a solid, that lithium bar is going to Li plus 1 electron. Now, I would like to point out something. You'd say, but wait a minute, the calcium needs 2 electrons. Correct, it does. So essentially what you need to do is make this a 2 to balance it out. So when we look at our final balance thing here, it's going to look like this. That's what it would look like when it's totally balanced for the electrons, I want to point out. Well, ladies and gentlemen, does it have any effect on the standard reduction potential? The good news is no, it doesn't change it one bit. Okay, so we have our lithium here. Let's look up our standard reduction potential for lithium. Remember, we're having lithium as a solid being made. Where do I have? Oh, here we go. Here's our solid, and they gave it as negative 3.05. But remember, because this is going the opposite direction, it's going to be plus 3.05 volts. Okay? That's going to be it. So when we look at our E cell, ladies and gentlemen, here we go. Our E cell is equal to the E of the lithium plus the E of our calcium. Remember, I picked these two totally different things, and you're going to get a total value of, oh goodness gracious, 3.05 take away 2.87. So our final answer, ladies and gentlemen, when basically we add those together, we got 0.18 volts for our calcium lithium battery. And maybe, guys, maybe that's why we don't have calcium lithium batteries. Maybe the lithium is combined with some other things, but certainly not calcium, because you're not getting a lot of electricity out of it. Not really. Okay, hey, so this is a basic run-through for standard potential. I hope you benefited from it, working with the 3 examples. They would provide this with you on the AP exam. And take care and have a good one.